Hello, FSharp. Welcome back. We are continuing our journey of optimizing a topological sort. I hope you're having fun. I still am. I love the challenge of taking FSharp, which is not traditionally known as a high performance language, and seeing just how much performance I can wring out of it. So I'm having a great time. Now, last time what we did is we changed the data layout of our graph type. And the reason we did that is for two reasons. Data locality. We wanted to make sure the data we wanted to analyze was all close to one another, and that way it increased the probability of it being in cache. And we wanted to reduce the number of objects that we were allocating. Before, we were using quite a few arrays for every node. Now our graph is just made up of 4 arrays. And technically not an array, it's a custom type that we're using. It wraps an array and forces the use of a unit of measure for the index. And so I have source ranges, source edges, target ranges, target edges. So reducing the number of objects that we're using, compacting the memory that we're working on, so that way the CPU has a better chance of making sure the hot data stays in caches. And when we did that last time, we saw a nice improvement in performance. We went from 897 microseconds to sort 1,000 graphs to 671 microseconds to sort 1,000 graphs. Now, you may recall from the beginning, our goal is to be able to sort 1,000 graphs of the size that we're interested in. I mean, it's not like arbitrarily large, so there are limitations, and we're taking that into account. We want to be able to do 1,000 in 500 microseconds. And if we achieve that, that gives us the performance that we need for the simulation that this topological sort is in the heart of right now. So we are really close to our goal. So this is exciting. Now what we want to do, though, is continue our journey. We want to profile and say, hey, is there anything else that we can do to increase the performance of this? And one thing I wanted to say is that we've seen some pretty dramatic increases in performance. And what I have found as I've done this is that each time you do one of these iterations, you think like, okay, well, this is maybe the last thing I can do. But the reality is what happens is it kind of opens your eyes to new possibilities for optimization. So for me, that's really fun to be able to see something improve by orders of magnitude. So I actually went ahead and ran the profiling of this method, this version that we have right now. And I used .trace. It's kind of my preferred tool. I'll reset it to what it looks like at the very beginning. So this is me. I ran it for many iterations and got sampling information about, okay, where is this thing slow? So now I'm going to zoom into it and understand what is going on. I go to main, which is the thing that's called profiling. And then I say, okay, what's going on here with the benchmark? My topological sort is the main thing. You don't need to worry about this collision that's coming up here. It's not actually a problem. So, okay, this sort, this is the method that is the topological sort that's running over and over and over again. And this is the thing that I really want to speed up. At this point, we're not seeing a whole lot. Like it's not telling us like, oh, there's a particular thing in there. It's just saying like, yeah, this method is the thing where you're taking all your time. It's like, okay, not terribly helpful. Expand out user code and say like, hey, is there anything going on here? It's just like, nope. You're doing a sort. Your sorting method is the thing that's taking all the time. It's like, okay, great. It essentially is 0 time in system code or the garbage collection wait, which is to be expected. We've done a lot to reduce the amount of garbage collection, the amount of objects that we're just using and allocating. Now, there's something interesting here that I want to point out is that now that something that's coming up is that we're spending 3.2% of our time in this call to array, where we're copying to another array. Okay, interesting. I mean, that's still not very much time, but it's like a big enough chunk that I'm like, okay, that might be interesting to try to attack. Now, I know that you can use spans, and if you're copying between spans, it'll use SIMD to make that super fast. But before we jump there, let's ask, like, why are we even calling to array? And I think that's probably the most important thing that I've been learning as I've been doing this kind of performance optimization work, is before I even try to like make the work that I'm doing faster, I ask myself, do I even need to do the work? Because the less work you do, the faster you go. And it's funny how many times like this has come up and up, and I'm just like, do you even need to do that step? Like, so get rid of as much work as possible. So let's go look at the code real quick and see, why are we making this call here to copy the array, just to understand it. So sorted nodes, we have this like to array here, and let's double check that's what this was talking about. Nope, it'll be here. Okay, member to array. So it's in this call. So, okay. So remember, we have our custom stack. So it's a stack allocated stack, and we wanted to use that so we weren't creating millions of queues and stacks that had to be garbage collected later. So we're just taking advantage of the fact that, hey, we don't need much memory. Let's just allocate something on the stack. We won't incur any garbage collection. Super fast, right? So that was like an optimization a couple steps ago. So now coming back here to the code, and it's this method here that's the slow bit. It's like, okay, this call to array is the slow thing. Okay. Now, could we make this faster? Yeah, we could, use spans and use SIMD to do this copying. But let's ask, do we even need to do this? Well, the reason we're making this call right now is because sorted nodes is how we are storing the result of the work that we're doing. The cons algorithm is basically saying like, hey, I'm going to create this list, this generic idea of a list, not an FSharp list in particular, but just like, hey, let's have this list and let's like add elements to it. And as we add elements to it, they'll be added in the order that is the topological sort. Okay. So up here at the beginning, we're using this to process stack, which is like, hey, these are the nodes that I need to analyze, and the sorted nodes, which are the nodes that I've actually done the work on. Now, why are we doing it this way in particular? Well, this actually comes from the direct translation I did of the cons algorithm. I went to Wikipedia, I searched for topological sorting. Cons algorithm is the first one that's in there, as you should be able to see right now, and this is how it prescribes doing the cons algorithm. Now, let's think about this. Well, one of the challenges that I have found when I read literature on high performance algorithms, it's typically written in very academic language, which can be very difficult to understand sometimes. It's also written in this kind of pseudocode format, which honestly looks mostly like Python, which is why Python's a great language, right? Like, because it's pretty quick translation from the academic pseudocode to the Python version. But the academic formulations are not as concerned with the performance on a particular machine. So there are some papers, but like for the most part, the pure computer sciencey papers, what they're thinking about is like, hey, on this theoretical machine, what would the performance look like? Like, what's the big O notation? What is the algorithmic complexity of this? Or what is the memory complexity of this? Like, how much memory would it need in theory? And it's not necessarily taking into account the hardware it's going to run on. So when I looked at this, I took what was there and pretty much copy pasted what was there without thinking much about like what work is actually necessary to do this. And again, as I've gained more experience, I now question that a lot more. When I look at these academic descriptions of algorithms, I say, okay, here it's saying like, hey, I have this I have an empty list L. Let me go ahead and zoom in a little bit for you, just so it's a little bit clearer. I have this empty list of elements that will contain the sorted elements L, and I have this set of all nodes with no incoming edges. And again, it says, okay, it's a set. Like, again, this is not F-sharp list. This is not F-sharp set. It's like the mathematical idea of a list and the mathematical idea of a set, or the computer science idea of it, right? It's the theoretical idea of these things. And then it's describing this while loop. We're saying, okay, well, I'm going to take a node N from S, which is the set of all nodes with no incoming edges, and then I'm going to add that to L, and then I'm going to look at the children of it. I'm going to remove the edges from it, and then I'm going to say, like, hey, for all the children, do those children no longer have any incoming edges? If not, I'm going to insert them into S, this set here. Okay, I took that and I pasted it. Is that the most efficient way to do this? No, and it kind of gets back to the idea of the array and why I'm calling toArray in the code, because I am using these two separate places to store, hey, these are the nodes I need to work on, and these are the nodes that are actually sorted. And I want it to be really fast, and so I'm using the stack allocated memory, but do I really need to do that? Do I really need to do that? Do I really need two separate lists? The idea is that, like, I have the sorted nodes that I've already worked on, and then I have some more nodes that I've yet to process, but I know that they're going to go in there in that order. I just haven't looked at their children yet. That's really all that's like differentiating between these sets of nodes. Ones that I've already added and I've removed all their edges, their outgoing edges. And then there's the ones where, like, I know they're going to go in this order, but I haven't removed their outgoing edges yet. Why do they need to be separate lists or arrays or whatever? Like, why do they need to be two separate collections? They don't need to be. And what would be really nice is if I don't have to call the toArray at all at the end. It'd be nice if, like, when I'm doing the work, that by the time I'm done with the work, it's in the thing I want at the end. Huh. What if my way of getting away from calling the toArray is to just, like, have the array be the thing I'm working with the whole time? What would that be like? So in our new version, let's try getting rid of those stacks, those stacks altogether. So I'm going to come down here and show you what that looks like. And I know we're kind of getting into some crazy town with the F-sharp code. This is looking less and less F-sharpy. I don't know why the syntax highlighting isn't coming on. Come on. Okay, cool. We're back. So this is looking less and less F-sharpy, or like what I would say is idiomatic F-sharp. But then I would also say, like, F-sharp is a very flexible language. It has some really nice defaults, but it also has escape hatches. It has ways for you to do the crazy optimization stuff if you want to do it. It's just going to make you work a little bit harder to do it rather than have that be the default. Like immutability by default, for example. You can make stuff mutable, and I'm doing it right here. And that's why all my mutable stuff has this kind of like orangish red color, because it's like, okay, Matthew, if your code isn't working, it's probably this stuff. It's probably the stuff that's mutating, because that's the stuff that typically goes haywire on you. So this is me taking advantage of F-sharp's flexibility for speed. That's how I'll say it. So how have things changed? The graph type has not changed at all. That has stayed exactly the same. Now, though, what I'm going to do, instead of using the two different stacks for tracking the to process and the results, as was prescribed in the cons algorithm, I'm not doing that. I'm going to have a single array that's going to be my result. And I'm using this GC allocate uninitialized array because I know I'm going to overwrite all these results. So I don't care if there's stuff in the array already. I don't need it zeroed out. So this is me telling the runtime, saying like, hey, just give me an array of this much space. I don't care if you zero it for me. I don't need it zeroed. So I'm getting the result. And now what I'm doing is I'm saying, okay, I'm going to have this array and I'm going to have two different indexes. One index will be, hey, when I need to add a node, what's the next empty spot? And the other is, hey, what's the last node I actually did the cons algorithm loop on, right? And so as I process the node, I'm going to move that index forward. So that's the result count. I'm going to move that forward. And so when I add nodes to the result, I'm going to move next to process index. And when I've processed those by removing their outgoing edges, I will increment the result count. And so that's how I will keep track of, have I processed everything or not? Instead of having the two separate collections, I'm going to have a single one and just use two different indexes that I'm moving along. And then what that means is that remaining edges, yeah, I'm just going to check here. So yeah, if the remaining edges, which means this is how I'm keeping track of the edges in the graph. If I have removed them all by the end, if there are still edges in there, I do not have a topological sort. There are still like things connected, and so I wasn't able to find it. So if there's still edges left, then I have no result, right? I cannot give you a topological sort. There are cycles there in somewhere. If all the edges have been removed, then yes, I can give you this array back, which is the sorted order of it. And so this optimization is about, we're doing the same work. Essentially, the algorithmic complexity of this has not changed. We're we're using less memory. We're not allocating as much, even though it's stack allocated. I mean, there's still allocation that's happening there. And we're working with less data physically. Instead of having these two different arrays, we're just working with one, and we're using these indexes to move along. So we're doing the same work, but with just less memory overall. And so will that increase our performance? Well, let's go to the benchmark and see what we get. Turns out we get about a 10% boost in performance. And this is just from being a little bit more clever. This is essentially an optimization of using less memory. And when we use less memory, it is easier for the CPU to keep the hot data in the cache because it's not using as much cache space. And we can see that by the cache misses, where it's saying, hey, previously this had 38,000 cache misses for 1,000 sorts. So 1,000 graphs, 38,000 cache misses, which means approximately 38 cache misses per topological sort. And that has dropped down. It's now dropped down to 27. And this is the kind of thing that you would hope for when you reduce the memory footprint of your algorithm. Cache misses are super expensive, more expensive than branch predictions. I mean, they're both not great, but a full cache miss, which means it's not L1, L2, or L3, it has to go all the way out to main memory. That can be just murder on performance, depending on how tight your loop is, some other aspects. So what's nice is that we said like, hey, we want to use less memory. Hey, we don't want to have to do this array copy anymore. And we think that if we make this optimization where we're using less memory, we should see an improvement in performance and an improvement in cache misses. And that's what we see. Okay, I hope this is kind of useful to you as I kind of work through what my thought processes are and how I try to improve these algorithms. What's really exciting here is that we are so close to our performance goal. So that is very exciting. My next video is actually going to be covering some work that another person did as a proposal on how to enhance this version of it. So that's going to be very exciting. So We got about 3 more videos in the series. We're going all the way to version 12, and I'll show you. We will see. Can we reach our goal? Can we beat our goal, and by how much? So thank you very much for spending some time with me. I really appreciate it. I hope you find this useful. If you have any questions, please feel free to comment or to email me. I'm also on the FSharp Slack and Discord, so please feel free to hit me up. Thank you very much, and you have a great day. Bye-bye.